Salazar, and I'm a PhD student at INCIBIO in Tucumán, Argentina. And this presentation is entitled Membrane Cholesterol Influence on Acetylcholinesterase Inhibition by epigallocatechin 3-O-gallate, EGCG. And it contains some of the results I've got during my PhD under the supervision of Dr. Carlos Minac. As a short background, we have proved in the past that EGCG does inhibit more efficiently to the membrane-bound acetylcholinesterase than to the solubilized form. But since the phenolic compounds are able to penetrate the membrane bilayers of liposomes in a cholesterol content-dependent way, we wanted to analyze the possible role of the membrane cholesterol content on the inhibition of the red blood cells acetylcholinesterase by EGCG. For this purpose, I've used the GOES, which are the membranes derived from the red blood cells after getting rid of the cytoplasmic content using a hypotonic lysis. And as all the membranes, the GOES are very complex systems that contains lipids, polysaccharides, and proteins. And among the last ones, we will find the acetylcholinesterase bounded to the membrane via a GPI. And I've used two types of GOES, ones with higher and ones with lower cholesterol content, and I got them after treating the control GOES with cyclodextrin. So as part of the results, as we can see here, the inhibitory activity of EGCG is influenced by the cholesterol content of the membrane, and that difference was higher when the membrane was treated with 3 millimolar cyclodextrin. Then we proceeded to analyze the interaction of EGCG with the hydrophobic core of the membranes, measuring the anisotropy of the dye DPH. As we can observe, the membrane packaging induced by EGCG was enhanced in the membranes with lower cholesterol content. In order to analyze the interaction of EGCG with the interface, we use the dye octadecyl rhodamine, which will sense the surrounding area of the interface. And we perform a quenching experiment of the fluorescence of the rhodamine by EGCG. And as we can see here, when the lower the cholesterol content, the more intense the quenching was, or the higher the values of the Stern-Bolmer constant. And this is probably because the lower the cholesterol content, the dye becomes more accessible to the EGCG. An extra analysis of the interaction of EGCG with the membranes was done using infrared spectroscopy. Here, as you can see, there are the spectra, the infrared spectra recorded for the two types of GOES in the absence and the presence of EGCG. So we analyze again the hydrophobic core by examining the methylene stretching vibrational mode. We only found a shift of 0.5 wave numbers with the low cholesterol content GOES in the presence of EGCG, but this change is in the same magnitude of the one produced by heating up the sample from 10 to 45 degrees, so it can be considered significant. We show again that EGCG perturbs the hydrophobic core of the lipid bilayer. But as this table shows, there is only a slight increase in the contribution of the hydrogen compared to the non-hydrogen bounded carbonyl groups to this stretching vibrational mode. So this means that EGCG produces only minor changes on the hydrogen level of the interfacial region of the GOES membranes. Therefore, it can be proposed that the hydroxyl groups of from the catechin may replace the water molecules as hydrogen donors in the hydrogen bonds formed between the carbonyls in the lipids and the EGCG. So we can conclude that the reduction in cholesterol content did enhance the inhibition of the acetylcholinesterase by EGCG, and that this reduction allows a greater insertion of EGCG in the membranes, and consequently the R18 dye becomes more accessible to the EGCG that acts as a quencher. And also the insertion induced a ordering effect on the membranes. And finally, that minor changes on the hydration level of the interface were observed, and this may be caused because the hydroxyl groups of the catechin may replace the water molecules as hydrogen donors. Thank you very much for your attention.